All right, I believe we are live. It'll take a second or two for it to actually start up on the Weights and Biases YouTube page. So give us just 1 second for that to kick off. All right, we are going. All right, welcome everyone to the Weights and Biases Deep Learning Salon. I am your host, Charles Fry. What we'll be doing this time is hearing from a bunch of Weights and Biases community members who participated in the Reproducibility Challenge. So the Reproducibility Challenge started off with papers with code, and we've decided to join that, help out with it. Actually, rather than me telling you anything about it, I'm going to hand it over to our Reproducibility Challenge expert at Weights and Biases, Diganta Mishra. Diganta, go ahead.
Hello, everyone. My name is Diganta. I'm a machine learning engineer, and as Charles stated, I'm glad that I can take the title of Reproducibility Challenge experts, but the experts will be doing the talking after me, the people who participated in the challenge. When I joined the team last year, coming from an academic background, Reproducibility Challenge is something that I really held with high importance because it's super important to make research in deep learning more transparent and reproducible. And we decided at Weights and Biases that we'll be supporting the Papers with Code initiative for Reproducibility Challenge. And we provided our participants with the resources to ensure that we could reproduce as many papers from top AI conferences from 2020. Um, and we did that with a fair share of success. We had so many interesting reports that we gathered from our participants who reproduced super exciting papers ranging from genetic algorithms to attention models uh, to many other variants like pruning and lottery ticket hypothesis that you'll hear in a short while. And before I before I give the mic to the people who participated in the challenge, I just want to give a super quick teaser trailer that we'll be also doing the spring 2021 edition of the Reproducibility Challenge starting off in April 1st. And I really encourage everyone to consider participating because it's going to be super awesome, and we are upscaling our efforts in helping you all out to make this a huge success. With that, I'd like to give it to the participants.
All right, yeah, I think first up we have the team that worked from the fast AI community that worked on the reformer paper, one of the most exciting of the many papers that came out this past year on making transformers more efficient. So Arto, if you'd like to take it away.
Hey everyone, my name is Arto, and I will be presenting our entry to Reproducibility Challenge for Reformer, the efficient transformer paper from Google Research, authored by Nikita Kitaev, Lukasz Kaiser, and Anselm Levskaya. And it's done by fast.ai community, represented here by my teammates Morgan and Halvar. So since the release of Attention is All You Need paper, transformers have become by far most popular architecture for NLP, and now is successfully applied to vision, time series, and audio data. And key mechanics in transformers is attention, which is used to produce contextualized token embeddings. And for each token, keys, queries, and values are computed, and then every key is compared to every query to produce the attention scores. And this results in quadratic complexity of the computation. And this is the main limiting factor to applying transformers to the tasks requiring attention in a long context. So making transformers more memory and time efficient is an active area of research right now. And one can refer to long-range ARENA benchmark for comparison of the current techniques. So the one we were reproducing is Reformer, which is designed to allow training on input sequences of length of over 64,000 tokens on a single accelerator. And to achieve this, 5 key techniques were used. So the LSH attention mechanism is an approximation to full attention using locality sensitive hashing. It utilizes the sparsity, like natural sparsity of attention metrics. So all the key query pairs are hashed using random projections, bucketized, and in such a way that similar key query pairs will end up in the same bucket. Then buckets are sorted. The keys and queries are sorted by buckets, and the attention scores are computed within each bucket only and into one neighboring bucket. This allows to reduce the time in memory complexity of the computation from order n squared to order n log n. And this is a randomized algorithm, and its robustness might be improved by doing multiple rounds of such hashing. The next technique is reversible layers. It's a variant of residual layers, allowing to avoid storing intermediate activations during the forward pass in cost of recomputing those at backward pass. And this enables to train very deep models under constrained memory requirements. And also there are some supplementary techniques. So for LSH to work properly, we need keys and queries produced from a single token to end up in the one bucket. And to ensure this, keys and queries are computed using shared projection. Also, to avoid feed-forward computation becoming memory bottleneck of the system, it might be computed in chunks, and when combined with reversible layers, this allows to control memory consumption by feed-forward layers. Also, to reduce memory used for storing positional encodings for very long sequences, XL positional encoding technique might be used, which uses factorization to enable very long sequences. So the central claims of this paper are following. The reformer performs on par with traditional transformer models while being much more memory efficient and much faster on longer sequences. And to verify these claims is the main goal of the reproducibility challenge. And the original implementation of Reformer was done in Trex, which is based on JAX framework. And our community emerged from fast.ai. So we had additional goals to re-implement the model in PyTorch and train it, adapt it to train using fast.ai training loop. So the memory and time complexity related claims may be verified by direct experiments. And here you can see memory profiles for variants of 6-layer deep models. And as one can see, there are this memory allocation jumps associated with big attention matrix computations for full attention. And also memory is accumulated during the forward pass and only released during the backward pass. Using LSH attention allows to avoid these memory peaks by doing it in n log n memory complexity instead of quadratic one, and using reversible layers allows to make memory allocation constant in regard to number of layers in the model. Here it's shown in orange. And the resulting reformer model, which is shown in red here, has by far lower memory consumption as compared to the classic transformer. And this will be even more strong when the context length grows. Also, notice that the memory consumption of reformer grows linearly with a number of hashing rounds, and this results in some accuracy memory trade-off. The next plot shows the computation time for LSH attention, and it is constant with respect to sequence length and grows linearly with number of hashing rounds, while the full attention computation grows approximately exponentially at our observation. So now to the next part. To verify the performance-related claims, there are three groups of experiments, one on synthetic task, text compression experiments on NVCate, and translation experiments on WMT14. So the synthetic task may be formulated as follows. Given a twin sequence of this form, where a word is a sequence of 511 random integers, the task is to predict the second half of the sequence in autoregressive manner. And this may be simply done by copying from the first part to the second part. The task is trivial to transformer with global attention, but it is infeasible if attention is local. Our experiments verified that LSH indeed attends globally, and we were able to achieve high accuracy on this task with 4 hashing rounds. Also, we observed unstable convergence when using shared QK projection on this task. And here you can see a bunch of runs which only differ in random seed, while like classic transformer converges very stably on this task. And next to the ablation studies, which are done on text compression using NVCate dataset. We compared each of the modifications with baseline model, and here you can see validation bits per character for shared QK transformer and for reversible transformer on this task. And for both experiments, we observed worse performance as compared to baseline. Also, we did experiments with encoder-decoder architecture, comparing classic and reversible transformers on WMT14, and the results are consistent with those observed on NVCate. And There are a number of possible explanations for the discrepancy of results we observed with the paper. One, the most obvious, is it might be that classic model is just superior to the modified ones, but also, as you saw in our experiments, the training did not fully converge. So maybe given enough time, the models will end up with the similar final score. And also we put substantial effort to obtaining a strong baseline. And we had restricted time for doing supplementary experiments on the modified models. And although we used the hyperparameters from the paper and original source code, there are a number of possible numerical differences in the framework or subtle implementation details, which result in some impact on the performance of the models. Also, as shown before, the random factor might play some role here, and it might be just due to some random variation. Also, we compared performance of LSH attention with different number of hashing rounds. And as claimed in the paper, the LSH attention with 8 hashing rounds performed very similarly to the full attention. And in our experiments, 4 hashing rounds were enough to reach similar results, but with somewhat slower convergence. So that's all with the experiments done. And I also wanted to highlight some tools which made our reproducibility experience much smoother. In NBDev is a tool for library development using Jupyter notebooks. It allows automatic code export to PY files, documentation auto-generation, writing tests in the notebook, and using them for continuous integration with GitHub, as well as running locally. So just a great thing to have in your toolkit. And also, weights and biases were really useful for fine-tuning hyperparameters and debugging some subtle things when you can like examine all the training dynamics and gradients during training. That might be really useful. Also, it's really useful when working in distributed teams such as ours. And it's really a pure joy to watch a bunch of runs progressing simultaneously when you're done with your implementation, and only running experiments is what's left to do. So to summarize, we were able to validate the memory and time complexity reduction is a reformer, and it indeed allows to train models on unprecedentedly long sequences. Also, the performance figures were not as good as in the paper in our experiments, and results from other papers also shown that the reformer did not perform just as good as a classic transformer. And this may be attributed to the fact that the reformer implementation is technically elaborated and might be difficult to reproduce correctly. So on that, thank you for attention, and we can proceed to questions.
Great. So thanks so much for sharing your work, Arto. And yeah, if the other folks from the team also want to pop up on video for just a few questions. The thing I wanted to start out with was asking So you mentioned that you had like a pretty big team, or that Weights and Biases was really helpful for your team, and I noticed that you had quite a large team of people on this project. So could you talk a little bit just about, how you spread work around the team, like what different people were working on, how you coordinated as what appears to be like kind of a worldwide and large team of ML engineers?
Yeah, I could maybe take that. Yeah, it was actually a challenging thing. Part of it that we mentioned in our report as well, kind of structuring it in a way that everyone could work on something and didn't have to ping, someone else to ask what they should be working on. So we used, initially it was all in Discord, and it was just a lot of messages and pinned messages and like task lists. We moved to Trello, which worked better, but also requires like a lot of maintenance and really requires like a kind of a champion to, make sure everyone's moving their cards along the board. So in terms of like task management, I don't think, Arto, maybe you might disagree or maybe not. Like, I think we'd like to try GitHub projects. Maybe I don't think Trello is the right solution for us. But yeah, we were trying to find a way to make it so that like team members who weren't, able to commit like a lot of time could jump in at any point, see a task that needed to be done, and go run with it without like too much input from anyone else. So open to hear any potential solutions. I don't know, Arto, if you have anything else to add.
Yeah, definitely. Having this task management tools integrated into your workflow flawlessly is really important for such team as ours. We had a bunch of guys who wanted to participate, but sometimes it was difficult to effectively allocate the tasks. Anyway, I think it was a great learning experience for everyone involved. But there is definitely a place to improve in terms of this project management.
Yes, I also think, as you mentioned, NBDev was helpful in this respect. So having like a proper development process with Git branching, pull requests, and sort of having a better development process also helped a lot. In the first part of the project, it was a bit chaotic, and we might possibly have a repo that we had to leave behind and move to a new one.
It happens, definitely. It's interesting, yeah, how much that coordination problem rears its head once you have a group of people. Diganta had a question. Diganta, if you want to speak up.
Yeah, first of all, awesome presentation. I have been following the space of transformers, and obviously it has been in the trends lately in literally every domain, not just NLP, but in CV as well. So just a general question, more from an academic perspective. You stated that the results you obtained from running the experiments with Performer weren't as good as the classic transformer model itself. So do you have any plans of extending some more investigations into why, and maybe do you have any future ideas around taking inspiration from what Performer did and maybe coming up with something of your own? I think that would be really a cherry on the cake to actually be able to manage that.
Actually, there are like a couple of directions it may progress. First off, we after finishing this reproducibility challenge, we created a repo to implement more modern techniques related to improving the efficiency of transformers in different directions. Also, this reversible layers might be really a cool trick, as they are kind of more efficient for particularly transformer architectures as compared to regular gradient checkpointing, for example. And it would be great if we could make it work just as good as the regular residual layers, although they are not quite mathematically equivalent. So it is possible that there would be some difference in implementation needed to make it work just as good. So yeah, and there is really a lot of new research published almost we can say every week in respect of the efficient attention. And I think it's really fascinating because now transformers are widely applied to tasks other than NLP, and sometimes really very long context is necessary to achieve great performance.
Mm-hmm. I wanted to talk a little bit more about this gap between the results that you found and the results reported in the paper. It seems very plausible to me. I think all the explanations you put out there were very plausible. So if you had to pick one explanation to go with, is there one that really stands out in your mind as the most plausible, or do you think that it's too uncertain?
Well, I don't know how others would say, but I would go with some subtle implementation details. Actually, we had some fun weekend with Morgan trying to debug really a minor thing, which is it doesn't matter mathematically, but you need to fix it to really make a model. And the performance difference was really consistent, while it just does not follow from the mathematics. And it's really hard to find this information of why does it happen. Also, there is a variant of implementation of efficient attention, which is not very time efficient, but memory efficient, which is done in chunks. And when done in PyTorch, it works while being just exactly mathematically equivalent to regular attention, but it works just worse out of the box. And I'm pretty sure it's possible to make it work just as well as full attention, but it requires some fiddling with these numerical things. And I would most probably attribute the differences we observed to these factors.
Yes, and also the reformer is sort of a much more finicky architecture than the transformer itself. So I think also it's much harder to tune it properly. So I guess if you spent more time and compute on proper tuning, we might have been able to squeeze extra performance out of it.
That's interesting. I think that kind of points. Often there's like a subtle phenomenon over the course of years, usually, where architectures and techniques that are really robust to implementation noise, architectures and ideas that find themselves in a very smooth part of the landscape of ideas, end up being a lot more successful than ones that, even though they work very well, if the landscape around them is very sharp, kind of like bad local minima or something. I also noticed that one of the things about the reformer model that seemed particularly kind of strange to me, and I noticed it was also in the reviews on OpenReview, is this shared key query component of it. Could you talk a little bit more about sort of why that's necessary and whether that's maybe an important part of this performance gap?
First, probably to most simpler question, why is it necessary? Well, actually, as it was shown, for locality sensitive hashing to work, you want to both keys and queries for the same token to end up in the same bucket, because attention is only computed within the bucket. And this is like this necessitates this shared computation. Also, like probably multiple recent papers shown that in some way transformers might be, and particularly attention, might be viewed as like lookup tables here. So we do lookups into the data, like not like directly in SQL way, but more like to some stored representation of the data. And basically this it can, like this view on the attention can give you an intuition why shared QK should work. On the other hand, we like when we share a QK, obviously by far the highest attention score would be for the token to attend to itself. That is why in Reformer the self-attention is masked. So the token is not allowed to attend to itself, but only when it cannot attend to anywhere else, right? And as transformer architecture is done, this makes like this disallowing self-attention might make a flow of positional information a bit more difficult through the models. So that's my idea about that. And probably that's why we observe such like strange results in regard to like effect of random seed on that synthetic experiment we showed, because that synthetic experiment particularly requires this good attention to positional information. We just need to copy a bit from particular position into the output. And for shared QK, that turned out to be like more difficult.
That's interesting. And yeah, that's a neat connection to make between that result that you had on the synthetic task and the issues that you saw on the more realistic tasks. All right, so I could talk about this experiment all day, but unfortunately we've got to move on to unfortunately we've got to close this off, but fortunately it's to move on to our next experiment. So thanks Arto, Halvar, Morgan, and everybody else in the Fast AI community who worked on that project. Thanks so much for your work.
Thank you for inviting us, and thanks everyone for your attention.
Mm-hmm. All right, so now let us switch over to, we have Varun and Rajat here, who worked on the reproducing Utku Evchi's paper on the RigL method. Varun and Rajat, are you here?
Yeah, we are here, and we can start if you like.
Yeah, go ahead.
All right. Thank you so much. Let me start. Just let me know if you can see my screen, then I'll begin.
Yep, go for it.
All right. Thank you. So, hi everyone. I'm Varun, and I'll be presenting our recent reproducibility work. I'd like to first thank Charles and the W&B team for hosting us today. I'm also joined by my co-author Rajat, and both of us.
Yeah. Hi everybody. I am Rajat.
And both of us graduated last August from the Indian Institute of Technology, Madras. So let's begin. A very prominent characteristic of deep networks today is their incredible overparameterization. Routinely, deep networks have parameter counts far exceeding data points. For instance, on the right, we have 3 models trained on ImageNet. Each of their parameter counts is clearly greater than 1 million, which is the size of ImageNet. This trend continues to grow today, especially with newer models such as transformers, especially the one we just saw transformers from the previous team. Compressing deep networks is therefore an important topic for both training and deployment. Sparse networks are a compelling choice to achieve this. Unlike a dense network, most of the sparse network's weights are set to 0. Such networks can be computationally and memory efficient. They can make it possible to train larger models with limited hardware. Typically, sparse networks are obtained via pruning, a process where you iteratively remove small magnitude weights. Unfortunately, pruning almost always degrades performance. In light of this, I'd like to introduce the lottery ticket hypothesis, which I could say is arguably one of the most interesting yet accessible works in recent sparse learning. So the idea is to identify sparse networks, or we call them tickets, that can be trained to attain performance similar to the original dense network, so you don't lose performance. The trick lies in how these networks are initialized. To do so, we first train a dense network and prune it. We now take this sparse network and reinitialize it with the original untrained dense weights. Unfortunately, this whole process is costlier than a dense network and sort of nullifies the computational benefit of sparse networks. So we want to do something better than this. RigL, short for rigging the lottery, tries to do something entirely different. They try to directly train a sparse network from scratch instead of pruning a dense network. And RigL achieves this by 2 steps. They first, every certain number of steps, they prune a number of weights and they grow the exact number of weights back. More importantly, RigL does not alter the number of non-zero weights in each layer. So if you remove 2 weights in a layer, you always add back 2 weights, but you may add it at a different place. This ensures that the floating point operations of the network are always constant, which is something that we desire. So let's talk briefly about the connection updates. And more specifically, RigL prunes the smallest magnitude weights, which is typical of pruning. And for growing, we grow the largest gradient magnitude. The growth strategy is exactly where RigL differs from other methods. For instance, set grows weights back randomly, and SNFS uses the largest momentum, where momentum is your accumulated gradient. SNFS, in addition to this, also tends to redistribute layer-wise sparsity throughout training, which results in non-constant flops. As a result of their growth strategies, these 3 methods have very different gradient requirements. For instance, set does not require dense gradients throughout training. You can get away by supplying only sparse gradients. RigL requires access to dense gradients every k steps or so when you perform this topology update. SNFS, on the other hand, requires dense gradients throughout training. So the only benefit you get from SNFS is the sparse forward pass. You don't really get any benefit through the backward pass. Let's now move on to the main claims RigL makes. RigL makes 2 claims. The first is that it outperforms existing direct sparse techniques, which is basically set and SNFS, compared at the same parameter and flop count. The second claim is the more interesting one. It matches or exceeds pruning when trained longer. Now, this is important because previously, all these direct sparse techniques were always inferior to pruning. And RigL manages all of this while maintaining constant training flops. This is also where we come in. We reproduce RigL from scratch in PyTorch, and we open source our code on GitHub. So let me go over the claim validity. I'll give you the results right away. Like there's no suspense. The claims are true, which is nice. But it's not true for parameter count alone. On this graph, you can clearly see that SNFS outperforms RigL for the same parameter count. You also need to consider flop count. When considering flop count, RigL performs the best trading off parameter count and flop count. Now, the more interesting claim is, does it perform better than pruning when trained longer? And the answer is yes. You can see that when we train RigL twice as long to match the computational cost of iterative pruning, we can achieve performance that is equal or slightly greater. So RigL, so far, we've seen a lot of good stuff. So let's see a few caveats. The first interesting caveat is that the initialization matters more than the method. What do I mean by initialization? So we start off with a sparse network, and I still haven't given you a recipe of how to get that sparse network. Initialization is exactly that. The authors use 2 initializations. The first is called random, where the sparsity of each layer is set constant. It's equal to the global sparsity, except for the first layer, which they keep dense. The other initialization strategy is called the Erdos-Renyi kernel, or ERK for short. And here the sparsity is nonlinear. It tends to allocate more density or less sparsity for layers with smaller capacities. So you'll see all these shortcut layers which have nearly full density. All right. Let's see what the implication of these initialization methods are. On both datasets, we make comparisons on CIFAR 10 and CIFAR 100. Switching to ERK initialization for any method always boosts performance. And the surprising aspect is that this performance boost is often greater than swapping methods. So for instance, if I were to swap between SET and RigL, I may get a performance gain of say 0.2 accuracy percentage or 0.3 accuracy percentage. But if I swap from random to ERK, I'm going to get a 1% increase. This sort of gives you, this sort of puts in perspective whether you should be focusing your research on new algorithms or you should be focusing on new initialization strategies. The second caveat is, so far we've spoken about all these nice flop benefits while maintaining accuracy, but the truth is you have no real benefits on current hardware. So why is that? The reason is CUDA does not efficiently support sparse operations at this point. CUDA does support certain kind of sparse operations which are block sparse, that is they have a certain structure to them. But in our case, we do not have any structure. So CUDA doesn't really offer us any speedups. This is in fact an ongoing research direction. So we might see things change in a few years from now. But the more positive news is that there are a class of processors such as the graph core, which support this really, really efficiently. On a graph core, having a sparse network would give you the exact theoretical benefits that we have stated so far. These processors are completely suited for fine-grained parallelism. So they can perform tasks that require really different kind of workloads. They won't suffer any performance degradation like a GPU. And in fact, there's a RigL implementation on this on GraphCore, and you can find it in GraphCore examples. This is one thing that I really liked about RigL because they have actually gone ahead and tried to test their algorithm on a processor which supports sparse implementation. The third caveat is quite actually related to the first. So what do we actually care about? Do we care about flop count or do we care about parameter count? I think a couple of slides ago, I said that ERK is better than random when you're considering a fixed parameter count. Why don't we invert that question? What happens if you consider a fixed flop count instead? We get a very surprising result, that is ERK is worse than random on a per flop basis. Now, if you put together caveat 1 and 2, it means that before you come up with a new method, like say RigL set SNFS or a new one, or a novel initialization scheme, you need to clearly define what your goals are. If you care only about flop count, like say you want computational benefits alone, you don't really care about storage benefits, then maybe you should be doing something different. All right. I'll briefly describe a few additional findings we found in our reproducibility work. The first is that RigL is quite robust to its choice of hyperparameters. What do I mean by robust? I mean that the two parameters RigL requires, which is this alpha and delta t, where alpha is your pruning rate and delta t is the update frequency, the frequency at which you will perform these topology updates, can be set largely independent of both sparsity and learning rate, which is nice because now you don't have to tune n+2 parameters. You can set these two parameters independent of everything else and just tune your remaining parameters. This does not add a burden on a practitioner. RigL can benefit from redistribution. So recall that I mentioned that in SNFS you have this concept of redistribution where you move sparsity across layers. That is, sparsity for a layer does not remain fixed throughout training. So we asked ourselves the question, what if you incorporate that in RigL? So it turns out that it can bridge the performance gap between ERK and random, but it considerably shoots up the computational cost and probably isn't the way to go about bridging the gap between ERK and random. You can find more details about these experiments on our paper. So let me now present a one-slide summary of our RC 2020 journey. So our initial impression was that each run on CIFAR 10 usually took us 2-3 hours, at least from the TensorFlow repository that Utku and authors had open sourced. So we expected that we'd probably take around 2-3 weeks to wrap up. In reality, with all the configurations considered, the hyperparameters, it took us a couple of months. So that was a good thing to remember. So a brief timeline, we spent, I think, the entirety of October getting our implementation correct. There were always points where we figured out that we had missed something, especially pertaining to sparsity of the gradient and momentum buffers. We then spent a couple of months experimenting on CIFAR 10 and CIFAR 100, as well as conducting these extension experiments. And the main challenge in our work was the volume, the sheer volume of experiments. So we spent a good amount of time thinking how best to represent these experiments. We did not directly just want to write down a bunch of metrics. And here are a few goof ups. So there was this time when I think we had to throw out a week's worth of experimentation simply because we forgot to consider random seeds. And turns out that random seeds was pretty important in this whole work, and we had to average across multiple random seeds. Flop counting was tricky. We also found that SNFS was costlier than what the RigL paper reported, which is also very different, which is quite unusual. You don't usually see a baseline being reported better than it is on a paper. And in terms of structure, so as I mentioned before, the main challenge in this reproduction was the sheer volume of experiments. We had to adopt certain tools to manage our runs better. First, we found Hydra to be super useful, particularly for composable configurations. As you can see on the right, experimenting with different methods just involved swapping YAML files. So we could experiment with different data sets, masking strategies, optimizers. We also found Hydra's multi-run format and support for hyperparameter tuning, especially packages such as Optuna, to be really useful. Hydra is a pretty new and extensible library, so I would highly recommend checking it out if you haven't used it before. Second, we started making use of technology from, I think makefiles come from the 80s and 90s, but turns out they're much more useful than bash files for storing experiment runs, storing the commands used to run those experiments so that you can quickly replicate experiments or make minor changes in case something goes wrong or you want to run variants of these experiments. Finally, W&B was really useful in terms of its dashboard that allowed us to easily group and visualize experiments. For each method, we had to run 3 or 4 seeds. As you can see on the right, these numbers 3, 6, 5. And there were a bunch of such methods. So for CIFAR 10, I suppose we ran around 150 methods, different configurations of these masking strategies, all of that. And W&B's centralized dashboard allowed us to easily visualize these. And initially we were using TensorBoard, but the moment we started performing more experiments, it became super unwieldy. So we switched to W&B where all the runs show up in a single place. And it was a much nicer alternative. The API support also helped us plot. So every time we made changes to our runs, we didn't have to go and manually replot. We just probably reran a Python script which did our plotting. And here are a few takeaways. So the first is reproducibility can be as fun as working on new ideas and is certainly important for the ML community. Authors aren't adversaries and will often be interested and invested in your reproducibility efforts. They want to see that their paper actually works when used in different contexts, different scenarios. And reproducibility need not stop at replication. Indeed, you can discover some overlooked findings, or you can even spawn new ideas. We'd like to thank Utku and the other RigL authors for their responsive communication throughout. We had a pretty extensive mail thread with the original authors. We'd also like to credit Tim Detmers. We built our code base by extending his open sourced SNFS code. You can find our code base on GitHub. You can read our report on archive, and you can also find our entire set of training experiments on W&B. So thank you so much for your time, and we'd be happy to take any questions.
Great. Thanks for sharing that work with us, Varun and Rajat. It was also, I love the tool stack that you had there with Hydra, weights and biases, and make files.
Yeah, we didn't expect the make files to show up. Like make files were an ad probably in December when we started we started putting all our experiments together in one bash file or something, and it got really long.
Yeah, I actually used a make file for my PhD dissertation. It was make thesis to set it up. So I appreciate the make file. So a couple of things. One, like on the more sciencey side, you mentioned that you implemented redistribution. So actually, if you could go back to that slide where you showed comparing random and then random with redistribution and ERK.
Yeah, let me in fact show you a bigger figure. That might help.
Perfect.
So, right, let me just share it. See, I've just blown up the figure.
Yeah.
So, all right. So,
yeah, so it looks to me a little bit like, maybe it's not a perfect lineup, but it does seem like the redistribution methods, which are in green and red in this chart, are basically learning the Erdos-Renyi kernel. Is that accurate, or am I missing something?
So it's far more extreme than the Erdos-Renyi kernel. And we had the same intuition. We actually suspected this. We actually wanted to show this result. We were biased towards showing this result that redistribution learns an ERK-like kernel because that makes that consolidates a lot of things. But the even more surprising result which we have is if you take this distribution and reinitialize a network from scratch, it doesn't learn. It performs really, really bad. It performs worse than static. In fact, I could pull up those results. So
that's interesting. That's wild.
Yeah, that's really wild. And unfortunately, we tried a bunch of things, but we weren't really able to explain this. And we
so
had a mail.
Like a very different phenomenon. Like the famous thing about lottery tickets, right, is that you can, if you take them
reinitialize it,
it works. Is that, and so you're doing the same type of reinitialization, right, where you keep the values of the weights the same, and like apply the topology at the beginning.
We tried both, in fact. We tried the lottery initialization and fine-tuning like initialization. That is, you keep the weights, you just resume training again. And both really didn't. The fine-tuning initialization works, but a lottery-like initialization does not work. So let me just share this real quick, if I can.
Sure.
Yeah. So one of the reasons this big table is not on the slide was because we didn't want to push off too many numbers onto viewers. So, so if you go to the last section, right, reinitialization with RigL SM, you will notice that the numbers are like 90.3 and 90.2, which is far lower than what you were getting before, 92 point something. And similarly on the CIFAR 100 column, we were getting 67-ish, and previously we were getting 72s. So if you were to take this trained initialization and perform a lottery-like reinit, it actually performs worse, which we found kind of surprising. Possible explanations are this extreme distribution. If you see this distribution, it's kind of extreme. Like it's higher than ERK. Like wherever ERK goes dense, it is dense, and wherever ERK is sparse, it is more sparse than ERK. So maybe this distribution is too extreme for you to reinitialize and train successfully. Maybe if you do some sort of a warm up before reinitializing, it might help. So there are these lottery ticket variants where you do a warm up and then you reinitialize with those weights. Maybe that could help. Again, this is just I'm hazarding a guess. So
yeah, no, that does make sense. I have seen those results about how important it is to sort of warm up before the lottery for like ResNets in particular.
And I think one more surprising aspect was that regardless, so I could start with random and do redistribution, or I could start with ERK and do redistribution. Turns out you end up with a very similar distribution, regardless of where you start. You could start with ERK or start with random. You end up with nearly the same distribution, and the computational cost just shoots up. This distribution, the computational cost is not due to redistribution here. The computational cost is actually due to the nature of this density itself.
Interesting.
And SNFS also has a distribution of this kind, which is what I alluded by saying when I earlier said that SNFS is much costlier than it seems.
I see. Interesting. On the topic, actually, I was going to ask another question, but I believe Diganta actually has one that he wanted to ask. Diganta?
Yeah, I have three questions, and this is a space that I really follow quite extensively. Not work on, but I do read literature on this. First question is, if it is purely on deployment level, considering the difference between RigL and SNFS, as you stated, SNFS is essentially fast and forward pass and doesn't do anything on backward pass. So if it's purely on deployment, which only concerns with the inference time or inference latency, which one do you think performs actually better? Is it RigL based networks or SNFS?
I would recommend going with just iterative pruning in that case. So if you like hover back to any of our tables where we have these results, you will see that the inference cost of pruning is proportional to the density. Like 0.11 is very similar to 0.1. SNFS, the distribution, the nature of the distribution makes a forward pass also costly. So for the same density, you would see like 0.38. So if you're concerned only about deployment, I guess iterative pruning is still your best bet today.
My second follow-up question is, this whole space looks pretty much similar to even, or maybe let's say synchronous and parallel to the space of neural architecture search, especially when you have latency constraints or you're trying to find optimal width. So there's this paper by Amazon, which was at CVPR 2020, called as Adaptive and Optimal Network Width Search with Latency Constraints. And just to summarize, that paper basically tries to find the adequate number of channels for each layer based on latency constraint provided. And there's an interesting graph in that paper which kind of conflicts the density graph that you showed. So in that graph, apparently it shows that the latter layers, like the layers towards the end of the network, requires to be more dense than the earlier layers. In fact, more dense, even more dense than the baseline density, while the earlier layers, and it's like linearly increasing. But in your density graph that you showed, the trend isn't looking similar of that sort. So just wanted to understand why would there be a conflict in that case, what the AOWS shows when they did a neural architecture search and what RigL or any other pruning method shows.
So I'm not sure how to really reconcile these two facts, but what I do know is that the fully connected layer of both these ResNet 50s and the wide ResNet 22 are set to 1. So the density of those fully connected layers are set to 1. These are really huge, like fully connected layers in VGG, for instance. I think it hosts around 70% of the parameters, and it's the last layer. So while it might seem that ERK and sparse gradient are actually like dipping density as you go deeper, for the fully connected layers, they tend to allocate full density. That is, you do not remove any parameters from those layers. So maybe that can be used to reconcile. Maybe we should try architectures where there is no fully connected layer and maybe then compare, because these fully connected layers tend to host a much higher number of parameters. So that could be a possible explanation.
Mm-hmm. And my last question is more on your implementation, which is just a general question. I haven't yet come to a realization, but why did you say that Makefile was more useful than a bash script in your case?
So let me put it this way. So for instance, let's say a single run of RigL on CIFAR 10, that would involve running at you had to run for densities, I think it was 0.5, 0.2, 0.1, 0.005, and two initializations. Then we also had these redistribution strategies. So it's like 2 into 2 into 5. We're already at a 20. And for if you were to do it in a bash loop, you could technically do it through Hydra's multi-run this syntax, which is kind of neat, but it sort of constrains you to a single device. And if you have a Slurm cluster to operate with, you maybe want to send some of these runs to different nodes. So we didn't really play around with Hydra's plugin for Slurm clusters, but what we did find useful was sort of wrapping it up in a bash script or makefile. And if you were to do it in a bash script, you would maybe have to loop over these variables or supply them using command line. And I feel that makefiles could do the same thing, but slightly more elegantly. And it was far more readable for the other person.
Makes sense. Thank you.
One question I had a little bit. You mentioned that there is actually a lot of subtlety to this like trade-off between flops versus parameters, like where you're getting your efficiency. And like my mental model there a little bit is like if you're designing for mobile devices, maybe what you care most about is reducing parameters. Whereas if you're like going for some super low latency setting, then maybe what you care about is flops. So like, I guess is that a good way of thinking about this trade-off here, or what have you learned while thinking about that trade-off in the context of this this set of experiments?
I think that's an excellent way to think of these trade-offs. So in my mind, at least, there are two communities in ML which use compressed networks. One is they try to train larger models on smaller devices. In fact, the linformer, reformer fall under these category. There's also this community of people who want to use ML for edge devices or ML to transmit data, ML to maybe even represent data, especially with these implicit kind of functions that we're seeing. So maybe they'd be concerned more about parameter storage as opposed to computational cost. So they'd be okay actually using a dense computational cost, but they want to save on they want to compress the number of bits transmitted.
Mm-hmm. Yeah,
I
that
have
makes
a
sense.
follow-up question. Just curiosity, especially. So two questions. One is, in an optimal setting, what do you care about most? Is it flops? Is it latency, throughput, or parameters? Now, I understand that you distinguish between parameters and flops, but flops is not always representative of latency or throughput. Some people might care about how many images it passes in a second, which essentially is the throughput. That is the first question. And the second question is there any alignment between the current state of the research in pruning with the state of research in quantization? Because that is also something very relevant to making neural networks being able to run on much lighter compute devices.
So that's a really interesting question and a really good one. So I'll actually answer the second part first. So I was briefly going through quantization literature recently, so I may have missed things. So like, please get back to me and let me know if I missed certain things. But the way I see it, I think there were 3 or 4 main approaches. One was range-based, linear-based, k-means, or Bloomier filters. And there are also these papers which use new lossy compressors to quantize. But most of them do pruning and then quantization. These quantization parameters may be trained, may be tuned, they're not really trained. And there's also this work where you do quantization aware training. But besides that, I don't really see works where quantization is done during training. You do it as a fine-tuning step to maybe tune some of these quantization parameters, but this is a work where you're doing pruning as you train. Even iterative pruning, for instance, you're doing pruning as you train. You don't do it post-training. So maybe once we start to see works where quantization is done during training, that could change things. You could use it in combination with pruning and get even more storage benefits. Now, the first question, which was what do you really care about, and are flops representative of throughput? I don't think the flops calculated here are completely representative of throughput. For one, we assumed there were efficient implementations of sparse convolutions available. So if I were working with matrices of so-and-so sparsity, I get the complete speed up in comparison to a dense model. To put this in perspective, suppose I had a layer which was 90% sparse, you would expect a speed up of around 10x. Whereas Q-sparse and CUDA-sparse and these block sparse matrices today will give you only around, I think, 3 to 4x. So these flop counts are not really representative of the throughput that you can achieve on a real device. But that is also where I find something like GraphCore exciting. You can probably try out these algorithms on GraphCore and benchmark the throughput there. That would be a good playing field.
Awesome,
all right, we don't have, we're basically out of time, but I did want to touch a little bit on what you just brought up with the GraphCore, their chips and the things that they make possible, because I think that's a really exciting direction of research. So it seems to me that like basically what's possible with that kind of a chip is just like much greater than what's possible with GPUs and TPUs. So do you think that that's something that might open up like sparsity like and pruning research to be like more useful, more widely done? Do you think that it'll have like a big effect on the kinds of ML research and ML like algorithms that we develop as a community?
So I'm pretty new to GraphCore as well, but let me just tell you what my initial impressions are. So I think the major bottleneck in GraphCore is the size of models that you can put on the processor. So for instance, GPUs go all the way up to 48 GB in memory, whereas these GraphCores are much smaller. I think you had the initial one was 256 MB, the later ones maybe around a GB. So if you can't put your model on these devices, you're not really going to benefit from the speedups. So that is one bottleneck currently. But yes, you're right. It should probably become a good platform for researchers to come up with new pruning algorithms, because you have this platform which can support fine-grained operations. So you should probably tune your algorithms to that.
Mm-hmm. Interesting. Yeah, it seems we had Sarah Hooker from Google on the Weights and Biases Salon to talk about the hardware lottery paper. I don't know if you saw that one, but it definitely expressed this idea that if we stick to our guns with like the existing stuff that works super well over time, we'll be constrained to like just have good ideas in that direction. We might be missing out on really cool ideas, like, for example, RigL in some sense like can't be fully deployed in all of its benefits or any of the extensions that you were working on without like a better compute substrate than what we have currently with CUDA and with GPUs.
Yeah, I think that's exactly the challenge the unstructured versus structured pruning committees are facing.
Mm-hmm. Cool. Right. So that is all the time that we have. So thank you so much for sharing your work with us, Varun and Rajat. And thank you to also, I think the Fast AI team is maybe still here. So thanks to both of you and to everybody who participated in the Weights and Biases Reproducibility Challenge. And we're going to be doing another one this spring, as Diganta mentioned. So folks out in the audience watching this video, if you want to join one of these, a team like this one, and make and reproduce machine learning research, join our community, join our Slack, and you can participate and do some really great and interesting work like these folks did. So Diganta and I hope to see you around as part of the Reproducibility Challenge or elsewhere in the world of machine learning. Take care.